Okay, next presentation. It will be an online presentation again. Boosting local recommendations with partially trained global model will be presented by Kexin Z.
Okay. Hello, everyone. My name is Kexin, and the topic I'm going to present today is boosting local recommendation with partially trained global model. So the proposed approach solves an issue in the context of cloud enterprise and recommendation systems. So in this setup, the data scientists would design the model, and it will be deployed to the recommendation system that is allocated for different tenants. The recommendation model will be trained with data owned by those tenants, and those tenants would then incorporate it and apply for their own use cases. So the challenge with recommendation system in enterprise solution is that it is unreasonable to assume all the tenants are similar. So their data typically varies significantly in size and quality due to differences in business strategy and operation setup. So this variation of data quality makes it very difficult to have consistently good performance for our recommendation system. The model needs to be designed to handle all kinds of data. So intuitively, if we can have all the data across each tenant pulled together, the recommendation system will be able to learn from all those different behaviors and thus be able to provide much improved outcome across the board. It is not going to work because of those following reasons. First, the same user may not have the same different tenant, may not behave in different tenants, and may even have the opposite preferences in the context of different brands. Next, having one recommendation system would generally raise the question of conflicting interests between tenants. And third, from the consumer side, they may want to keep their preferences and personas separated to different brands. It can be very hard to ensure that individual privacy is respected when pulling data this way. We need to have the overall recommendation system learn from different behaviors across all tenants, and at the same time emphasize individual tenants' characteristics and only use the user-specific behavior within that tenant to make recommendation system while respecting individuals' privacy. To tackle all these four requirements, we have designed a two-step framework called boosting local recommendation. So the first step of the framework is to train a global partial model. Instead of using it directly, the global partial model will then be added as a boosting step during tenant-specific model training to make up what the local data are lacking. So this framework should work with most machine learning models. In this presentation, we're going to use collaborative filtering as an example. The rationale behind collaborative filtering is that if a person A has the same opinion as a person B on an issue, A is more likely to have B's opinion on a different issue than that of a random chosen person. One way to implement collaborative filtering is with matrix factorization. It works by first construct a matrix of user vectors, consists of all of their known and unknown preferences. Then we decompose this matrix into two smaller matrices W and H, such that the product of those two matrices will closely approximate the original matrix. We call the first decomposed matrix user factor, and the other one the preference factor. So now let me illustrate how the local boosting framework can be applied in matrix factorization scenario. First of all, we will learn the global behavior by merging all data together and perform factorization at that level. This is similar to a simple data pooling approach except we are removing user identities. Next, in the boosting step, to incorporate global behavior, we first filter from the global partial model to obtain only the relevant records for the given tenant. Then we combine those records with the tenant-specific local data to form the target matrix to perform another matrix factorization at the local level. The portion we have retrieved from the global matrix will be able to carry the global behavior and influence the local recommendation. This approach works better. However, there are some additional issues. First, from an engineering perspective, the output of the global partial model process is very large, making it a challenge to maintain. Next, it is relatively hard to control how much influence do we want the global model to influence the local behavior, because the information carried by each rows in the global partial model are different. There are some additional privacy concerns too. The first point of EU's GDPR is the right to be forgotten, meaning that the user has the right to notify the tenant to have his or her data erased. In this case, upon user request, we know that there is probably a role in the global model that is specific to that user, but we don't know which. Secondly, California CCPA makes sure that we cannot complete user profile across tenant boundaries, unless it's an aggregation. The presence of user record make it subject to debate. Even those values are contributed by all values in the entire matrix. So these considerations motivates us to come up with a second approach. As you remember, the process produces two matrices, the user matrix and the preference matrix. We would treat the preference matrix as n linear models with respect to P features. Similarly, the user matrix obtained from the global factorization is the user's tenant behavior vector. And the preference matrix is a local recommendation model on those n linear functions. To boost the local model, we infuse the global preference matrix to the local one, and then use the user's local features to multiply the infused preference matrix to obtain the recommendation result. The global user factor of the user's global feature vectors are no longer required after we have obtained the global preference vector. With this approach, we only need to persist the global preference matrix. Since both P and N are very small, are way smaller than the number of users N, it is very easy to maintain a fixed size preference matrix as a global partial model and share it across all participating tenants. To control how much influence we would like to have the tenant's recommendation infused by the global behavior, it's very easy to control the infusion process by adjusting simple weightings between the two preference matrices. Most importantly, the model passes all of our ethics and the privacy guidelines. You can easily see that the end results of the global partial model, the preference matrix does not have any sensitive user data. As long as the number of users is moderately large, there's no way to infer any personal behavior from it, even though it is shared across different tenants. There's no way to obtain or infer any user behavior from other tenants either. One constraint of this approach is that the factor dimension P in local and global model needs to match. From a tenant point of view, how much it contributes to the global pool versus how much benefit it can get from it become interesting and important, especially for tenants that have a small user base or just started their business. Our approach makes it possible for any tenants to benefit from the global knowledge at a certain degree to have better recommendations. The degree can be the same across all tenants or proportional to the tenant's contribution, or even customized to suit business needs. Now let me let's see how this approach performs in practice. We have one user X that exists in both tenant A and B. In the first plot, you can see that the user have different behavior in both tenants. At a global level, they also have some other behaviors from other tenants as well. The second plot shows the comparison of the user's recommendation with and without local boosting in tenant A. It is clear that the user's local behaviors are preserved, but the boosted one also discovers some additional interesting patterns where we're not seeing in tenant A alone. The same can be observed for tenant B. Additionally, you could see that the recommendations for the same user in different tenants are sufficiently different. Here are the plots at the aggregate level of the two tenants. It shows that the local boosted model keeps the same shape after boosting and start to find additional recommendations at the local model that the local model might have missed. That's all I have for today. Thank you very much. Do we have any questions?
Thank you. Any questions? Maybe I can start with one question, actually. I wondered about the data set that you used to do those comparisons you mentioned. Can you tell us a little bit about if you have used like a data set for your experiments, or did you run some experiments by using a data set, and what is the size, for example, of the data set you used, if you used any?
Oh, sure. So the data set varies. In this system is one of our product called optimized send time. So it uses to recommend what's the best time to send out an email in our case. It varies from quite a bit. So we have about a few thousands of participating tenants from various businesses. So they varies from retail to gaming companies as well. Yeah, there are large ones and very small ones too. Like large ones could be up to billions of users, and smaller ones is like a few dozen could be.
Yeah, okay, thank you very much. And I see that there are questions in the room, so please.
Hello, thank you for the presentation. It was actually quite related to what we wanted to do. So I'm from Rundfunk, and we have multiple platforms, audio, video, articles. So we wanted to do similar recommendation, like a generic version of it, so we can use it for all platforms. But the problem we have is, I mean, as per my understanding, the model that you showed are like for collaborative filtering, but if we have, let's say, content to content base, and in that scenario, we have like multiple data types like video, audios, then how we can do the similar structure to have like generic as well as local, how we can divide the data in that format, and how the input model will work.
Yeah, sure. I think like we mainly focused on collaborative filtering at first, but then we started venturing into using other models as well. I think the main thing is that in generally we want like learn from the global level is that we just pull all the data together and put that into the model itself. And that kind of like when you're making the prediction, it's the user's behavior across everyone with no specific context to be aware. And then at the second level is how like it requires some thoughts into different models, but like the general idea is with that information, and then you can start to borrow some of the additional results you learned from there. And then with local ones, you're only using the specific local data. That's it. So the first approach is actually we just pass in some like the global level results and mix that with the local one, so that like you have some knowledge from there and retrain the whole model. So that's the easiest way we think it would work. But like depends on different privacy guidelines. That's you might want to tweak that a little bit.
Okay, and one more question I have is like how you deal with like the cold start scenarios where you don't have the data for a new user, or how, and this another thing is the history that you consider for training the model, like for a user, like for 30 days or for a year, how you like how you consider the data for it.
Sure. The first one, the cold start, it's hard. So with this scenario, you should have at least some data. Like it doesn't have to be a lot, but once we start to collect a little bit of data, we'll be able to use the global portion to start to kicking in. So the next question is
about the data
history, right? Like, yeah. So in our case, we mainly just keeps 90 days of data. So, but generally, like the longer you want, you have is probably the better. It's basically depends on your own situation. We keep 90 days because we want to like be able to forget, and it's easier to implement a lot of the GDPR concerns.
Okay, thank you.
Okay, thank you. I'm sorry, but there's another question here in the room, but due to the time constraint, we can't unfortunately take it. So please use the RecSys hub for your questions. Thank you. Okay, so our next presentation